Hi everyone, and warm welcome to the third and final part of today's seminar. My name is Linnea Suominiemi, and I'm the project manager of this year's Stockholm International Youth Science Seminar, or SIYSS for short. SIYSS brings young, prominent researchers from all around the world here to Stockholm to present their work for you in order to inspire and to help you improve and train in scientific English. SIYSS is organized by the Swedish Federation of Young Scientists, which is a non-profit organization that aims to increase the interest in natural sciences, mathematics, and engineering among youths. And apart from SIYSS, we also do summer research schools. We do Utställningen, where you as a high school student can compete with your high school project. We do cybersecurity project, teaching material, support associations around Sweden, and much, much more. So if you as a student are interested in learning more how you can participate in our events, or if you as a teacher want to know more about our teaching material, please visit our website ungaforskare.se. So, like I said, this is our third and final part, and we will be diving into the interesting world of machines, AI, and mathematics. Here we have 4 participants again, Joshua Shunk and Emirhan Kurtulus, both from Regeneron ISEF, Saloni Kwatra from Umeå University, and Sinan Deveci from Schweizer Jugend Forscht. These participants' abstracts, reports, and posters are also available on our website if you want to deep dive more into the projects and learn more about their research. And please don't forget to fill out our questionnaire. It is located next to the broadcasting, and there you have the chance to ask questions directly to the participants. You have time today, the 9th of December, until 4 p.m. to send in your questions. And with that said, I would just want to say enjoy the final part of the seminar.
Hello, my name is Joshua Shunk. I am a 12th grade student at Perry High School in the state of Arizona. I'm very excited to be here and to be giving you all this presentation today. Today we'll be taking a deep dive into machine learning, how it works, what is overfitting, and how it affects machine learning. Artificial intelligence is one of the fastest growing fields today. It can be defined by John McCarthy as the science and engineering of creating intelligent machines. Artificial intelligence can be described broadly as the perceived intelligence of all machines. Artificial intelligence is broken down into many different subfields, most popular of which, and what we'll be focusing on today, is called machine learning. Machine learning is a type of artificial intelligence designed to understand the relationship between inputs and outputs. Inside of artificial intelligence is deep learning. Deep learning is a scalable machine learning technique using neural networks and can be trained unsupervised, meaning without the use of labels. One of the biggest issues with machine learning today is known as overfitting. Overfitting occurs when a model becomes too familiar with the training data. As training data decreases, overfitting increases. You can see in this graph how the loss, defined technically as the measurement of how well a model is doing, or think of it simply as how poorly the model is performing, is decreasing at a much more significant rate at the training than the testing. There are many ways that a model can prevent overfitting. We call these regularization techniques. Regularization is the capacity and the complexity of a machine learning model. Some current machine learning techniques include L1 regularization. L1 regularization, also known as lasso regularization, is a form of feature selection. There's also L2 regularization, known as ridge regression. Ridge regression forces weights to be small, but not zero. It uses the sum of the square root of all feature weights. Developed by researchers at the University of Toronto, dropout randomly shuts off neurons, creating exponentially many different models. And finally, we have early stopping. Early stopping stops training when the validation loss starts to increase, meaning that the model is no longer improving and is becoming too fit to the training data. Now let's take a look into my research, neuron-specific dropout. So these are the most basic and fundamental equations to a machine learning model. But what do they mean, and what is R? Well, R is our regularization technique. Regularization and this function is known as neuron-specific dropout in my research. Unlike popular regularization techniques, dropout takes in 4 inputs: the layer input, the layer labels, the validation input, and the validation labels. By understanding which neurons have values farthest from the validation average, we can find the most damaging weights and drop them. Similar to dropout, applying neuron-specific dropout produces a thin network. A thin network is the product of all neurons that are kept after dropout. So how well did neuron-specific dropout perform? Well, it beat out traditional dropout networks and standard networks on all forms of data sets that I tested it on. You can see the significant decrease in the dataset size needed to train an effective model. What is most interesting is neuron-specific dropout's ability to tie the training and testing loss. Like I mentioned earlier, this is how we understand when a network is becoming too overfit, and we can see there is no significance between the training and testing loss. What's most interesting is neuron-specific dropout's ability to learn what neurons need to be dropped. We can see when we start training the layer, it is essentially dropping neurons randomly, similar to dropout. But as training progresses, the layer starts to understand what neurons are becoming damaging and consistently drops those. So neuron-specific dropout isn't perfect, and there are still many things to work on. Neuron-specific dropout is unoptimized, and it takes significantly longer to train than similar neural networks. Further, neuron-specific dropout simply drops a neuron for now. Future research could look into how neuron-specific dropout could alter a neuron to improve the performance on a wider array of applications and data sets. Now, I know algorithms of machine learning isn't as exciting or interesting as saying you developed the model to recognize cancer or drive a car, but these applications wouldn't be possible without effective algorithms. So hopefully this presentation gave you a brief overview of AI, and maybe someday you'll create your own AI model. Thank you.
Hi all, I'm Emirhan Kurtulus from Turkiye. I'm a freshman at Stanford University. Today I'm excited and proud to present my project, Deep Learning-Based Stereotactic Cranial Surgery Planning. We will go on a journey starting from operating rooms and ending at the development of an artificial intelligence-based army of doctors. Starting with my motivation, on the right side of the screen you can see a bar chart representing the number of deaths by cause worldwide in 2017, published by our World in Data. And it can be seen that approximately 20% of all deaths are caused by cancers and cranial diseases. And unfortunately, the mortality rate and the number of people dying increases. And when we turn to the Handbook of Neurosurgery, one of the most seminal books in the field, we can narrow down the reasons into 3 fundamental causes that are inadequate or incorrect surgical plan, late diagnosis, and lack of knowledge on neuroanatomy. To study these reasons and analyze the problem on spot, I have observed many cranial surgeries and patient diagnosis meetings. On the figure, I'm the person on the leftmost side. And I had 3 main key takeaways that are, despite all the advances in biomedical engineering, the success of all current methods solely rely on the experience of a neurosurgeon. And the best methods are determined by retrospective studies. I have personally observed 2 neurosurgery professors discussing over a patient for over 40 minutes and not being able to find a common ground. And it is also crucial to eliminate the human error as much as possible. And as a solution to all these problems, I created the following pipeline, where I try to replicate the thinking process of a neurosurgeon and plan cranial surgeries with minimal damage to the patients. What you see here on this pipeline clearly reflects how a neurosurgeon approaches the neurosurgical procedure planning. What a neurosurgeon does while planning is they take a look at the MRI images of the patient. MRI images can be thought as the pictures of the brain, just like X-ray, but with a subtle difference. They are in 3D. And what a neurosurgeon does is that they dive into two really important details. The first is that the problem in the patient's brain, and the second is the anatomical structure of the patient's brain. And to analyze a problem in the patient's brain, I use a neural network that I designed, which is currently the state of the art, to find and localize the tumor in 3D space. And then for further information and present the doctor with more information, I use another neural network for the classification of a tumor. And to really understand the anatomical structure of the patient's brain, I, again, using a neural network, create the anatomical map of the patient with over 155 anatomical regions and landmarks. And then I create a 3D tractogram of the patient, again, with the use of state-of-the-art neural networks. And tractograms can be thought as the nerve tracts in our brain, which we shouldn't touch during the surgery. And using all the information extracted by using a novel machine learning algorithm I designed, I plan and visualize a cranial surgery to the doctors. Starting with the tumor segmentation subproblem, I changed the convolutional blocks in the 3D unit architecture with MB cone blocks that are inspired by the efficient net algorithm. With this approach, I was able to scale the networks more deeply and widely with in a parameter efficient way, and thus have the state-of-the-art performance. And in tumor classification subproblem, I used a more aggressive data augmentation method and the new training methodologies such as sharpness aware training. And with this approach, I was able to achieve state-of-the-art performance with most of the models I tried for transfer learning. And for the tractography subproblem, I used transformer networks for the first time in the literature. And the novelty of transformers here is that I first extract 3D coordinates of the locations of the tracks, and then I evaluate the vectors from the MRI instead of using the coordinates by trilinear interpolation. This allows my model to be rotation invariant and outperform the current state-of-the-art significantly. And in the last subproblem, namely whole brain segmentation, I create a new multi-atlas reference points that allowed me to extend the range of data sets I used. And with this pre-training approach, my model was to outperform the state-of-the-art. And finally, the most important part being the cranial surgery planning. I use the convex sum of the regions that coincide with the tractography map and the anatomical regional importance map that were constructed by the neural networks I presented. And to allow flexibility of doctors' opinions on the importance of tractography versus anatomical landmarks, I allow doctors to use the coefficients to either prioritize the tractography or the anatomical regions. And finally, for the optimization of the pipeline that I introduced, I use the post-operation MRI images and compare it with the pre-operation MRI images. And then I find the location of the craniotomy. And craniotomy is the operation of drilling through the skull to access the brain. And then asking for the opinion of the neurosurgeon on how well the plan is, I backpropagate on the weights. And with this approach, I was able to optimize the system to present it to the doctors. And finally, on the application side, I developed two different applications. The application on the left is a desktop application that is presented to the doctors, and on the right side it can be seen an augmented reality application that for which doctors can use to practice the operation beforehand. And here you can see my references. And with that, my presentation comes to an end. Thank you for listening.
Hi everyone, my name is Saloni Kwatra. I am from Umeå University. My research project is about federated learning with decision trees. It is completely okay if you don't know anything about federated learning. I will explain now. What is federated learning? It is a collaborative machine learning framework. What is machine learning? Machine learning is used in a variety of applications to draw patterns or insights from data. Federated learning is a distributed version of machine learning. In federated learning, the data is scattered across multiple devices. Like here, we have mobile phones, which has the data. And there is an aggregation server. So in federated learning, all the data is scattered across devices, and there is no need to collect all the data at one particular location, which enhances the privacy. In the initial step, a global model is received by the devices. All the training of the model happen at the devices, and the devices share the model parameters with the aggregation server. The aggregation server, as the name suggests, aggregates all the model updates received from all the devices and sends those model updates to the devices. This process goes on until the model is converged or the specific number of iterations are completed. In this manner, a collaborative machine learning model is learned without sharing the data of the devices. So there are two advantages of federated learning. Firstly, the privacy of the users is reserved, and secondly, it is computationally efficient as no data is being transferred at one particular location. The objective of my research project. My research project is to perform federated learning with decision trees. Decision trees is a classical machine learning technique. It is basically how we human thinks in our real life. Suppose we want to play outside, so we will check the weather, if it is raining or not. If it is not raining, we will decide to go out. That's how decision trees models are built. In our approach, we perform k-anonymous federated learning with decision trees. So the aggregation is a very important step in federated learning, as the models need to be aggregated. So in our work, we studied how to perform federated learning with decision trees. So there must be a way to aggregate the decision trees learned by the distributed devices. So in this aggregation approach, all the devices share the nodes of the decision tree from the root node to the leaf node. Firstly, the devices share the root node. The aggregator finds out the most frequent attribute and creates the split branches. And this process goes on from the root of the decision tree to the leaves of the decision tree. Even though the data of the users is not being shared, only the model updates or the model parameters are shared. Still, we cannot say that it is completely privacy preserving. So we add another layer of privacy to our approach, which is Mondrian k-anonymity. It is a famous privacy model in which users' data is divided into groups of size k, such that each record is similar with at least k-1 other people. So it is difficult to trace back an individual from a database. This is the flow diagram of our approach. So we have D devices, each having its own data. First, we discard the uncorrelated features using correlation analysis, so to speed up the process of building decision trees. And then we apply Mondrian k-anonymity to protect each data, and we obtain the masked data. Each device trains decision trees on its data without sharing its data with any other user or the aggregation server, and sends those trained decision trees with the aggregator. The aggregator merges or aggregates those decision trees and send back to the devices. This is how we achieve federated learning with decision trees. So these are some of the results. On the x-axis, we have size of the K anonymized group. The more the size of the K, the more is the privacy. And on the y-axis, we have the accuracy of the aggregated decision tree. So the graph shows that even when we have more privacy, the accuracy remains in acceptable limits. So we can have both accuracy as well as privacy, as there is a well-known trade-off between privacy and accuracy. On one hand, machine learning is trying to uncover the hidden information within the data, and with privacy, we are aiming to protect the sensitive data of users. So with our work, we aim to have a balanced trade-off between the privacy and the utility of the data. The previous results was on IID setting. IID means independent and identically distributed. When the data is distributed among the devices in an IID manner, but this does not happen in real life. In real life, we have heterogeneous data. Each device can have completely different data distribution from other device. So we also tested our approach in a non-IID setting. And we found a certain drop in accuracy level when we did our experiments in a non-IID setting, but still it is in an acceptable limits as we increase the value of K. These are some of the future directions. So first is user preferences. What if different devices have different policies about sharing or not sharing its node? What if the partial decision trees are shared? If a device wants more privacy and only wants to share the partial decision trees and not the complete, as sharing decision trees with more depth can leak more information about the data of users. Now, approach 2 was about extracting the similar samples. Since federated learning is collaborative machine learning, so we can also extract the similar samples from the data of different devices and then perform federated learning. For extracting similar samples, there is a function, locality sensitive hashing function. What it does, it hashes the similar data into the same bucket with a high probability and the dissimilar samples into the different bucket with a high probability. Summary, we presented two approaches for performing federated learning with decision trees. Approach 1 performs the aggregation of decision trees shared by the different devices. Approach 2 first extracts the similar samples from the data of different devices and then performs machine learning. So this is how we achieved federated learning with decision trees. These are some of the references. Now, this ends my presentations. Thank you very much for patiently listening to me. Thank you.
Hej, jag heter Sinan och kommer från Schweiz. In my project, I investigated phenomena related to primes, means, and logs. Today, I'll tell you a bit about the log part. But let's start somewhere else. Everybody knows the Leaning Tower of Pisa. But have you wondered how far off it could lean before it would fall? As this is a mathematical talk, we will not talk about stones, but rectangles. So the question then becomes, how can we construct a tower that leans far out? How far out can it lean before it falls down? Now, you may be surprised to hear the answer, infinitely far. What? Let me show you. You can make such a construction, and the first thing that comes to mind is, well, normally we build bottom up, but now we build top down, right? We start with this block, and then, let's assume that all blocks have unit length, so they have length 1. And then after 1/2 comes the next block, so here the distance is 1/2. And then we have half of the distance, and put the next one down below, and then a third up to halfway point, and so on. And then the total overlap the total area that stands out will just be 1/2 plus 1 over 2 times 2 plus 1 over 2 times 3, and so on. So we get this. Now, you may see a pattern here. It's just 1/2 times 1 plus 1/2 plus 1/3, and so on. Now, this here is called the harmonic series, and it's quite important in mathematics. And it's also quite a beautiful series because it's really counterintuitive. Because you can see the individual terms get smaller and smaller, right? 1/4 is smaller than 1/3, 1 over 100 is smaller than 1 over 10, and yet you can prove that the series diverges, which means that it grows infinitely large. So we can indeed construct a tower that leans out as far as we would like. For example, like this. So we've seen that this thing grows infinitely large. Well, maybe we can do something with it. So let's just alternate minus, plus, and so on. That's called the alternating harmonic series. And if we plot this, well, then it oscillates, right? Because it's first 1, and then minus 1/2, plus 1/3, minus 1/4, and so on. And we see that it approaches the yellow line, which is approximately 0.69, which is surprisingly equal to the natural logarithm of 2. So we get this. Now, this result has been well known for centuries. But if you stare at this for as long as I have, you start to wonder, what's so special about 2? It should be possible to find similar series to do something to the left-hand side so that this 2 becomes a 3 or a 4. So to find series that correspond to logarithms of other numbers. Mainly something that is log 3, something that's log 4, and so on. Well, let's start with log 3. Well, we have to modify the series for log 2, right? Now, what did we do there that's somehow connected with 2? Well, we subtracted the terms where the denominator is even and added the terms where the denominator is odd, right? 2 and 4 are even, 1, 3, 5, and so on are odd. Or phrased in another way, we subtracted the terms where the denominator is divisible by 2 and added the rest. So if we want to construct a series for log 3, we just subtract the terms divisible by 3 and add the rest. So let's try this, right? 3, 6, 9, and so on are divisible by 3. We subtract them, and the rest we add. Nope. Why? Well, because we add more terms than we subtract. We add twice, and then subtract. Add, subtract. So it always gets bigger and bigger, and then it diverges. So how can we fix this? We add too much, right? But we have to add and subtract the same amount. So but we cannot subtract additional things because that would break the pattern. So let's just count the things we subtract twice. So something like this. We just change the weight from 1 to 2. Now we add twice and subtract twice. Let's see. It works. So we have found a series for log 3. And then I generalize this for log m. So this is the series that gives the natural logarithm of m for any m in the positive integers. You see, here are the terms we add, and here are the terms we subtract. And then I verified this for m equals 3, 4, and so on with the computer. But because it's mathematics, you have to prove things. Mathematicians love proofs, and so I have to prove it. Now, the proof I'm not going to show you, but it's in my paper. The whole paper is accessible here, so feel free to check it out. Now, the series may seem a bit complicated, but the first step was not. The first step was just we looked at this and asked ourselves, what's so special about 2? Can we generalize it? So essentially, we we have something. We took something already existing, and then we looked at it, analyzed what its parts do, poked it a bit, changed it, and saw how it reacts. And then we got our beautiful formula. And so maybe what I want you to take away today is that in order to arrive at beautiful results, you should ask curious questions and play around with things, no matter your field. Tack för att ni lyssnade.